Hello, my name's Sam Albert. This is my presentation from the IEEE Aerospace Conference 2023 in Big Sky, Montana. I want to acknowledge my co-authors, Dr. Doostan and Dr. Schaub. Today I'm presenting the work Onboard Density Modeling for Planetary Entry via Karhunen-Loève Expansion. So planetary entry trajectories are affected by a number of uncertainties. One of the dominant sources of uncertainty is variations in atmospheric density. They're highly sensitive to this, and atmospheres notoriously are complex and difficult to predict. In fact, it was Edward Lorenz, a meteorologist, who pioneered modern chaos theory and coined the term the butterfly effect because of how sensitive his meteorological predictions were to small changes in initial conditions. Now, in particular, atmospheres suffer from both epistemic and aleatory uncertainty. Epistemic meaning we don't have enough data to fully understand planetary atmospheres. This is still true at Earth, but it's especially true at destinations like the ice giants, Uranus and Neptune. And in addition, they are characterized by aleatory uncertainty, meaning even if we had an abundance of data, there's inherent random variability in the behavior of the atmospheres, including in the density profile across an altitude. So this figure I'll spend some time on because I'll be showing a lot of figures like this in this talk. The y-axis, the vertical axis, is altitude in kilometers, and the x-axis is normalized density perturbation. So this is just density less the mean value of density and divided by the mean value of density, meaning that a value of 0.5 would be a 50% enhancement to the mean. I'm showing a few sample profiles here. In this case, these are altitude profiles from a Mars atmosphere data set. And I'm also showing the plus or minus 3 sigma bounds in the solid dash or in the thicker dashed line. So we'll come back and talk in more detail about these figures. At this stage, the point is just these are very wide plus or minus 3 sigma bounds. There's large uncertainty, and that uncertainty varies with altitude, and there's correlation structure involved, all of that. Now, this is not an atmospheric science talk. We're not concerned with developing the best atmosphere model on the ground, and others have done that already, at least with the data that we have. But what I want to talk about is any onboard closed-loop guidance algorithm inherently requires some kind of onboard density model. Even if there's not an actual density model on board, it might be baked into the feedback gains. There might be a simple lookup table, but any kind of closed loop guidance requires some assumption about the density that you're flying through. And we've done this in the past, but we've always taken a deterministic approach to guidance. But there's an emerging set of approaches to stochastic guidance that rely on making predictions of not only the expected value of the state, but the state uncertainty at a future time and make control decisions based on that. So to do this, we need to revisit the type of density models that we would use on board a spacecraft flying through the atmosphere. So when it comes to uncertainty quantification, by far the most popular method is Monte Carlo. This is a method of random sampling that I'm thinking all of you are familiar with, and it's popular for a reason. It's very easy to set up, and it performs well even when the number of dispersed inputs is very high. As you can see from this equation for the expected mean square norm error, it converges at a rate of 1 over the square root of n, where n is the number of random samples. So that's a fairly slow convergence rate. And in some cases, we can do better than Monte Carlo, meaning that either there is a random sampling technique that requires a smaller number of random sampling trials, or perhaps doesn't require random sampling at all. One of the challenges, though, is that these non-Monte Carlo methods generally require the number of dispersed the number of dispersed inputs to be finite, and in general, it needs to be small because these methods suffer when that dimensionality is too high. And I've roughly ordered them in terms of as you get those increases in efficiency, you also tend to suffer even more from this so-called curse of dimensionality. So when I say stochastic dimensionality, I'm referring to the number of dispersed inputs. And all of this motivates us to seek a parametric representation of density uncertainty that has a low stochastic dimensionality. And that might enable us to make efficient onboard predictions of our state uncertainty. So most of the existing ways of modeling the atmosphere fall into basically one of two camps. On the left, on the simpler side of this continuum, we have an exponential atmosphere model. It's motivated by hydrostatic equilibrium. It's very simple. It's very low dimensional. It only has two parameters, surface density and scale height. However, this is a simplified model, so it's approximate. It might be unrealistic. It fails to capture the short period variations in density that can exist in atmospheres. Even if you're varying scale height, real atmospheres do not necessarily fall along an exponential curve. On the right-hand side of this continuum, we have sort of semi-empirical physics-based models. I'm calling them black box models here, things like IMSIS or GRAM you may be familiar with. And these are significantly more complex, and they're customizable based on inputs, including you could account for the season or for solar weather conditions. And they're either, well, they're much more realistic. But the problem is, first of all, the densities that they output they're sort of treating density as continuous. So the stochastic dimensionality would just be whatever the number of altitude steps you have in your output profile. And these are sort of black box models, so we're just treating them as, you can run them once and get a density out, but this is not necessarily something that's appropriate for onboard use. So our goal is to find something that's in the middle, that is higher fidelity than an exponential atmosphere model, but lower dimensionality than these black box models like GRAM. So we're seeking a finite dimensional parametric representation of the density profile, and that would enable the use of these other uncertainty quantification techniques while keeping a more realistic atmosphere model that includes a better accounting for uncertainty. So to do this, we're going to model density as a Gaussian random field. A random field maps some random outcome to a continuous function across space. And a Gaussian random field is a random field for which the joint PDF for any finite set of values in the domain Z is Gaussian. And so this is fully defined by its mean and covariance functions, as shown here. So I think a better way to visualize this for our case is I brought back the same plot of density. And so remember, we're showing plus or minus 3 sigma bounds across altitude. But then imagine we take a slice just at this one altitude of 50 kilometers, and we could plot a histogram from a bunch of trials from, in this case, it's Mars-GRAM, to look at the scalar value of density in each of those trials just at 50 kilometers. And we can also show that this histogram is well approximated by a Gaussian PDF. So that permits our assumption of a Gaussian random field. And you can sort of imagine stacking up, there's one of these PDFs for any altitude in this range. So we're stacking up an infinite number of these Gaussian PDFs, and they are correlated. They're not independent. So that gives us a challenge, because even though this is a theoretically appropriate representation, a Gaussian random field is infinite dimensional because, like I said, there's an infinite number of those PDFs that we're stacking up. So a solution comes to us in the form of a Karhunen-Loève expansion. This allows us to approximate a Gaussian random field in an optimal way. It's essentially a Fourier series expansion in that it is an infinite linear combination of orthogonal basis functions. And in particular, it's the choice of basis functions that minimizes the mean square error. So here's our Gaussian random field. We can see it's the sum of the mean function plus this infinite summation, where we can solve the eigenvalue problem for the covariance function to get the eigenvalues and eigenfunctions of that covariance function, and those appear here in our summation. So this is an exact representation of our Gaussian random field with an infinite sum. And then we can truncate that sum by ordering the eigenvalues in decreasing order. And we can truncate that based on some acceptable level of relative mean square norm error. Finally, these y sub I variables are random variables. This is where the randomness enters our equation. And it turns out that in the case where the random field is Gaussian, these y sub i's are independent and identically distributed standard normal variables. Okay, so that's a KLE, and I've presented it in a continuous form. We're going to apply it just in a discretized form. The setup is very similar. And as our truth model throughout this presentation, I'm going to use the Global Reference Atmospheric Model, or GRAM, for Mars. You could use any model, though. This is sort of model agnostic, as long as you can generate a large set of sample profiles. So we'll generate 5,000 of those sample density profiles and generate the sample covariance matrix from that data. And then we can take the eigenvalue decomposition to get the eigenvectors and eigenvalues and use that to set up our Karhunen-Loève expansion. And unless I specify otherwise, we're going to truncate to just 15 terms. So only 15 of those eigenvector eigenvalue pairs is going to form our entire summation plus the mean function. Excuse me. So what I'm showing here is in green, I have the sample profiles and 3 sigma bounds for GRAM. So this is our truth model. That's what we're trying to approximate. And in orange, I have sample profiles and 3 sigma bounds for the Karhunen-Loève expansion, or KLE. Now, you might notice this is not a particularly good approximation, and that's for a few reasons that I'll get into in a moment. But one of them is that we've chosen a very small number of terms. So if we increase the number of terms sufficiently, we should have a very good approximation, but I'm setting the number of terms quite low because it will be a better basis for comparisons that I'm going to make later in this presentation. And I'll also point out that you can see it's performing really well here at low altitudes. And then very quickly, it's capturing a lot of the variability here. And then above about 50 kilometers or 40 kilometers, it's capturing almost none of the variability. It performs very poorly at these high altitudes. This is because we perform the expansion on the value of density itself. And density is orders of magnitude larger near the surface than it is at these high altitudes. So with this small number of terms, the expansion prioritizes variability where the absolute values are large and almost entirely ignores it at higher altitudes. So much of the rest of the presentation is focused on, we've introduced the KLE, but how else could we construct it so that we can get a more useful representation of density variability? So one of the steps we can take is, in both of these cases, the plot is showing normalized density perturbation, but there's a difference in how I've actually constructed the KLE. So on the left, this is the same plot as earlier, and the KLE is built on density values themselves. On the right, the KLE is constructed using the normalized density perturbations. And you can see that it does a much better job of capturing density variability at these higher atmospheres, but it fails to capture almost any variability at lower atmospheres. This has almost the opposite problem of what we had earlier. And for a similar reason, the normalized variations are much higher at high altitude, so it prioritizes there and misses a lot of the important variations we have at lower altitudes. So at this point, we'll introduce a couple of reference vehicles and trajectories that we'll use to motivate some further developments. The details aren't super important here, but I'm showing a couple of different examples. On the left, we have a small probe that enters Mars's atmosphere and coasts until landing, with a couple of deployment events near the end. And on the right, we're simulating the Mars Science Lab aeroshell, but instead of continuing on to parachute deploy and landing, in this case, we're flying an aerocapture trajectory. And for the purposes of this presentation, you just need to note that that means it flies into the atmosphere, dissipates energy through atmospheric drag, and then skips back out of the atmosphere on the other side. And so that's why you can see this dashed orange line is showing velocity versus altitude. It comes in at a given velocity, gets down to maybe 45 kilometers altitude and loses a lot of speed, and then exits the atmosphere again. And in the blue solid lines, I'm showing the dynamic pressure pulse for each of these vehicles. The reason I show this is that our aerodynamic force is proportional to our dynamic pressure. And that gives us a sense of, the region of altitudes where we experience this dynamic pressure pulse is the region of altitudes where it's most important that we are accurately capturing density and its variability. So we can use this as a guide to tell the expansion where to focus the most. So on the left and in the middle, I have the examples I showed, or excuse me, on the left, I have the example I showed earlier, building the expansion based on density. And then in these two other cases, we're forming the KLE by taking density, computing the normalized perturbation, and then multiplying that by the reference dynamic pressure of the vehicle. So again, we're essentially informing the expansion where it should focus its efforts. And you can see that that does work. So we have very accurate representation in this region where the dynamic pressure pulse exists. It's a little bit lower in the case of the shield vehicle. It's a little bit higher in the case of the aerocapture. And below and above those key altitude ranges, we don't capture the variability as well. And again, that's because we've chosen a pretty small number of terms in order to make these comparisons. But so far, I've just been talking about how well are we representing density itself. But an important thing to note here is we don't care so much about modeling the atmosphere as well as possible. What we really want is to accurately predict dispersed trajectories through the atmosphere. So we can make a comparison on that basis directly by taking those reference trajectories, dispersing the atmosphere, and running a 5,000 trial Monte Carlo analysis. And we can compare results with the truth GRAM model with each of these versions of our KLE. And you can see that normalizing based on dynamic pressure, which is the version shown on the right, is much more accurate at capturing in this case, the parameter I chose is peak heat flux. And that's relevant because that occurs near the peak dynamic pressure pulse. And we're capturing that much more accurately with this model than we do with models built on density or normalized density perturbation with the same number of terms. Additionally, I'm showing the density versus altitude profiles themselves in the region near peak dynamic pressure for the air capture trajectories. And you can see that they are characteristically more realistic in the case of normalizing by dynamic pressure. They're very smooth in these other cases, so they're not capturing these important short period oscillations in density. So everything I've talked about so far has assumed that density varies only with altitude, but that is not actually the case. And if we want, we can construct a KLE that treats density as a function of altitude, latitude, and longitude. And the way that we do this is actually quite simple. You can take an ordered set of indices along any multidimensional domain, and you can simply reshape that into a one-dimensional array with the same ordering. Then you can construct your covariance matrix, develop your KLE as before, generate a realization, and then you can just reshape in the other direction to get back a realization in that same multidimensional domain. So we can do this for density. In this case, it's just going to vary with altitude and longitude for easy visualization. And I'm showing the normalized perturbation here in this color scale. And on the left is the truth model. On the right is a KLE, where in this case, I've chosen the number of terms based on capturing 99% of that variability. And you can see that they appear quite similar, but it's important to note that 99% variability translates to requiring 884 terms in the expansion in this case. There's far, far more than the 15 that we've been using up to this point. We can again compare this on the basis of predicting trajectories. And so on the left, we have the truth model where altitude varies with altitude and density varies with altitude and longitude. And in the green here, we have our KLE representation, and you can see that it's a very good predictor of the truth model. On the right, however, we have a KLE, and this is using 50 terms, so still a lot more than the 15 earlier, and it's doing a very poor job at predicting our peak heat flux, both the median value and the uncertainty bounds. And you can see part of why in the plots of density profiles themselves that I'm showing here. We're in the lower right, we have the 50-term KLE expansion, and you can see just visually that it has much less variation than the other cases. I'll also note that the orange case here is running the truth model, but I'm ignoring variation with longitude. And that still is a pretty accurate representation of peak heat flux. So what that tells us is that in the truth model that we're using, the longitudinal variations are not actually very important. But despite that, when you construct a KLE from that data, it requires a very large number of terms to accurately reconstruct this multidimensional domain. So some brief takeaways from this: it is possible to set up a three-dimensional or even higher dimensional KLE. And so you could have an onboard model that predicts uncertainty based on both altitude, zonal, and meridional variations. However, it's likely not worthwhile for an onboard model. So it's important to consider variations across time and across space other than just altitude when you're doing vehicle analysis, performance predictions, ensuring you can meet requirements, all of that. But it doesn't necessarily need to be modeled on board. It's likely good enough to have an updated best estimate of your nominal and uncertainty bounds on a columnar atmosphere and not represent these other variations on board. But it depends on the mission of interest, of course. Now, for any onboard density model to be truly worthwhile, we need some way to update it using information that we gain while flying through the atmosphere. In other words, update it from noisy measurements. So we can do this for the KLE, and it turns out if you treat the densities across altitude as the state vector, then assume that you're measuring density at your current altitude. Well, then in that case, your measurement is just a linear function of the state. And we've already assumed Gaussian distributions for density, and we can reasonably assume Gaussian distribution on our measurement noise. And as a result, we can simply apply the Kalman measurement update equations to make an update to our mean vector and to our covariance matrix that are predicted for our KLE expansion. So here what I'm showing is in the dashed blue line is the prior mean, and the prior uncertainty is the shaded blue region. So you can see that's just following right along 0 for normalized density perturbation. And we're flying through a true profile that's in the dashed green line. And we take 5 noisy measurements that are shown with the black X's and sequentially ingest them using this Kalman equations. And the posterior mean is the dashed orange line, posterior uncertainty is the shaded orange region. And you can see, as you would expect, that the posterior mean goes near but not exactly through these noisy measurements, and our uncertainty decreases a lot near the measurements, and it decreases some near but not exactly at those measurements, and then it decreases basically to its prior value far from those measurements, and this is all according to our prior assumptions about the correlation structure in the atmosphere. So our prior information tells us that there's not a very strong correlation between perturbations at 80 kilometers and 50 kilometers altitude. And so we just regress right back to our prior mean in that case. And so this plot would look different based on your prior assumptions and the noise level, but this gives us some way to make onboard updates. I do want to note a remaining challenge that is left open so far in this work, and that is that, okay, we've set up a way to make onboard updates, and the Kalman equations are one thing, but then once we have a new covariance matrix, we would then have to recompute eigenvalues and eigenvectors to get our new KLE representation. And this is potentially a large, maybe 200 by 200 size of covariance matrix. So an open question is there some way that we could modify these equations to directly update the eigendecomposition instead? You could potentially do this by taking advantage of the low rank nature of the covariance matrix, meaning it's not a diagonal matrix, but values far from the diagonal should be close to 0. We don't have any clear paths to this yet. We have a couple of ideas, but I would be open to discussing with any of you if you want to email me, because this is currently an open-ended challenge for us. Some quick conclusions. I talked about how stochastic guidance approaches make onboard predictions of state uncertainty, and KLE gives us a simplified model of density variability based on some reference data that can enable those onboard predictions in an efficient way. We compared different ways of constructing that KLE and showed that normalizing density perturbations and then scaling by reference dynamic pressure is the most compact representation considered here. We can, if we so choose, construct the KLE in a 3D sense to incorporate other regional variations in density, but this is likely not worth the added complexity for onboard use. We also showed a way to incorporate noisy density measurements via a Kalman formulation to be able to update our KLE as we fly through the atmosphere. But efficient computational implementation of that setup is a remaining challenge for this work. So I just wanted to show an example here of atmospheric variability. So these two photos are taken about an hour apart. In the first, you can see very clearly across toward Gallatin Peak here from Big Sky. And on the right, from basically the same location, you can barely see the very nearby Lone Peak. So I just thought that was a fun example of a relevant atmospheric variability for all of us who are here in Big Sky, at least in person. Thank you for your attention. Please send me an email if you have any questions or would like to discuss. And thank you.